Babbage difference engine. Charles Babbage's difference engine was the first design of an automatic digital computer. The machine would have created error-free mathematical tables by steam power. Making a table with the machine would first involve finding a proper polynomial function, something of the form y equals c sub 0 plus c sub 1 x plus c sub 2 x squared plus c sub 3 x cubed, etc. The proper polynomial function would accurately approximate the desired function in the table. After the 18th century work of Taylor, Maclaurin, and others, finding a good polynomial became fairly easy. Here is an example of a square law function roughly approximating a sine function. Once the polynomial was found, it was transformed into an even simpler form by the method of finite differences. With Babbage's difference engine, the first values of the polynomial function and its differences are entered on the dials, and the difference engine cranks out the rest of the desired table by repeated additions. Here is an example using x squared plus 5x plus 7. The function is calculated for the first values and differences. The first column adds 1 to itself to form the x value of the table. The rest of the columns hold the differences. Here the machine is ready to run. To get the next y value, each column is added to its neighbor. Here is the first cycle. Here is the second cycle. The first and second columns are the part printed in the table. Babbage could not get the machine built. As with most original research, he had a better design before the first machine was finished. Then he had an even better design. Then he ran out of money and got into a fight with Joseph Clement, his machinist. The machine was too expensive, and the existing tables, while containing errors, were judged good enough. It was too difficult a project for 1840. Digital computers are difficult to build. Today, the difficulty is hidden in factories with million-dollar cameras and microscopic cleanliness, but it's still hard. Countries have been bankrupted trying to build them. In 1840, calculation not done on paper was done by some sort of analog calculator. Analog devices, where the number is represented by an angle, a length, a weight, or a voltage, have always been easier to build and use. In most cases, an error of less than 1% in a calculation is all that's needed. Analog devices do that easily. Galileo's sector, combining angles with lengths, is probably the simplest analog calculator. The slide rule is next in simplicity. Areas on a map can be measured with a planimeter, a wheel or skidding mechanical integrator. The planimeter's wheel integrator was adapted to make automatic computers of several sorts, culminating in the mechanical differential analyzers of the 1930s. The mechanical analyzers were used to make tables and plots. The mechanical differential analyzer's wheel integrator was replaced with the summing amplifier's electronic integrator in the 1940s, and the electronic analog computer dominated science and engineering. The government, Wall Street and universities had the absurdly expensive digital computers, while everyone else had the much cheaper analog ones. For the price of a television set, an engineering firm could get work done with a simple and intuitive device. Programming in the analog world means connecting modules together in a way that represents the problem. The programming is simple and intuitive. Every problem is visibly different. The wires hook to different things. Here is an analog computer for solving x squared plus 5x plus 7. The analog computer is still with us, hiding in many forms. The op-amp summing amplifier still amplifies. The 741 op-amp, invented in the 1960s, is still being made. The analog computer, by giving a different view of mathematics, still has value. A little more about digital computers. Babbage's difference engine would have made mathematical tables by addition of base 10 numbers. The ENIAC computer of the 1940s was a programmable electronic version of the difference engine, mostly adding and subtracting base 10 numbers. Its best use was for making tables. The ENIAC was built to do the work of the analog differential analyzers, a differential analyzer with 10-digit precision and the ability to store 20 numbers. To program it, modules were connected together by wiring, just as in the electronic analog computer. The later fully functional computers, like the EDSVAC, were programmed from memory locations. A fully functional computer programmed from memory locations is said to be Turing complete after Alan Turing. Neither Babbage's difference engine nor the basic ENIAC were Turing complete. A Turing complete computer has to be able to change the program steps based on the results of calculations. The two most important ideas are the loop and the branch. A loop in a program is movement backward to do some steps over. A branch is movement forward, skipping some steps. This is the simple beginning of a vast universe of computer science stuff, so I won't go further here. Thanks for watching.